I'm interested in this course for ulterior purposes. I guess we're far enough along, I can be honest with you. So I've got an abiding interest in Earth's tectonic evolution. And I've um, made it clear what I think about how Earth's tectonic evolution, and I've dragged Matt along in some of this. And basically, it is that Earth hasn't always had plate tectonics. Now, the geological community is resistant to change, like all communities. It's made up of human beings, and they like the way that they understood the Earth, and we've seen this over and over again. And that's independent of whether the Earth's tectonic history needs to be reinterpreted or not. But be that as it may, in the effort to understand Earth's tectonic history, mineral deposits play an important role because Earth's tectonics have a big role in what kind of mineral deposits form, and for that matter, what don't form. So I was very pleased to see that the textbook had a section on the temporal distribution of metallic mineral resources, because that was an important motivation for developing this course, was to understand better what kinds of mineral deposits there were, and then B, use that information to inform a discussion about Earth's tectonic history. And it goes both ways. Maybe understanding Earth's tectonic history helps the industry find more ore deposits. So I've been honest, and let's get into it. So what you're going to see is that Muller et al. Have their story, and I will comment on it in several places, and then I hope you will chime in as well with your opinions, because reconstructing Earth's tectonic history is a game for everybody, right? It's not, there's not one, you can't say, okay, that belongs to paleontology, or that belongs to geochronology, or that belongs to anything. It's like, this is the Earth's tectonic history has to explain basically every field, but certainly one of those fields is mineral deposit. All right, so the chapter starts off with an introduction. It points out that mineral systems involve 4 critical parameters: geodynamics, tectonics. There's fertility, right? You can't get blood from a turnip, so if you're looking for a porphyry copper, there better be a source of copper somewhere in the vicinity. The architecture of the mineral system, and of course, preservation. Once it gets eroded away, well, maybe you'll have a placer, but those don't last very long. So those are the 4 main elements in mineral systems, guiding our efforts to find some. And geodynamics is especially important for controlling endogenic mineral systems. And so we remember we could grossly subdivide mineral systems into endogenic, ones that are sort of controlled by Earth's interior more than the exterior, and exogenic, where the atmospheric. All right, so especially the endogenic mineral systems are of particular interest. But in discussing the temporal evolution of ore deposits, we are also getting information about the evolution of Earth's atmosphere and biosphere. So, tease out those 2 elements. Now, geodynamics and fertility are related for endogenic systems, and in particular, convergent plate margins have subduction zones, and the fluids that those generate are hydrous and sulfur rich, whereas rift and intraplate settings are more anhydrous. So the fluid is critical in an awful lot of endogenic systems. So the book, we agree that the geodynamics is especially important factor controlling mineral systems and mineral deposits. And the book says this is because although geodynamic systems have varied throughout time, their tectonic base has always been plate tectonics. And out front, truth in advertising, and I think Matt disagree with this statement. All right. So here are two different positions on this. There was a paper published by Brian Windley, passed away earlier this year, 30 years ago, uniformitarianism today, which is, of course, one of the important things we teach in intro geology is, the present is the key to the past. So he ripped off of that and said plate tectonics is the key to the past. So don't worry about it. It's always been plate tectonics. Now, I published a paper earlier this year that reinterprets the past 2.5 billion years of Earth's tectonic history into identifying 2 episodes each of plate and single lid tectonics. So that's controversial, and but the point is, you're going to be getting both sides of the story today. I'll try and do justice to their arguments, but I may lose control of myself. All right. So there is no agreement on Earth's tectonic history. So I asked ChatGPT, when do most geoscientists think plate tectonics started? I'd like percentages. And it answered this. Estimated start time of plate tectonics, approximate percentages of geoscientist opinions. Now, so here we've got the Hadean, early Archean, mid to late Archean, Paleoproterozoic, Neoproterozoic, or later. So 5 to 10% think it started in the Hadean, 20 to 30% think it started in the early Archean, 40 to 50% think it started in the mid to late Archean, 10 to 20% in the Paleoproterozoic, and the lunatic fringe, of which I'm proud to be part, thinks it started later, although there seems to have been an earlier episode as well. But we're not going to get into the details of that. The point here is this polling may not be accurate, but I think it's not completely off. I mean, that's kind of the feel I get from my colleagues about when they think plate tectonics started. So just so you know, this is an area of what we could call not settled science. All right. So there we go. Just to remind you of the geologic time scale of interest. So this is Earth history, the Hadean from the beginning to about 4, when we get the oldest preserved rocks. Right, we got zircons that are older than 4 billion, but not rocks. And then the Archean, which is a big chunk of Earth history, 1.5 billion years. And then the Proterozoic, which we can break into the Paleoproterozoic, the Mesoproterozoic, and the Neoproterozoic, is basically 2 billion years, almost half of Earth's history. And then the Phanerozoic, which we know and love. This paper I wrote was just about the last 2.5 billion years. I'm not in a position to voice an opinion on the Archean, and maybe never will be. All right, so let's talk about plate tectonics, since plate tectonics is kind of on the being tried here. But I worked with a geodynamic professor at ETH in Zurich, and we define plate tectonics to emphasize both its major driving force, which is oceanic subduction, and it's the fact that you have to have a mosaic of plates in order to have plate tectonics. Having 2 plates isn't enough. So we define it this way: a global tectonic system powered by subduction, in which the lithosphere is divided into a global mosaic of strong plates, which move on and sink into weaker ductile asthenosphere. 3 types of localized plate boundaries form the interconnected global network. You all know those. New oceanic lithosphere is created by seafloor spreading at mid-ocean ridges. Old oceanic lithosphere sinks in subduction zones, and 2 plates slide by each other along transform faults. And here's an important point. The negative buoyancy of old dense oceanic lithosphere sinking in subduction zones mostly powers plate movements. Okay, that's often missed. You'll see introductory textbooks show these convection currents making the plates move, but that's not the the opinion of the people who have really thought deeply about what drives the plates. It is the sinking of dense oceanic lithosphere that drives plate motions.
Well,
Yes?
and for example, and this has been presented for a long time, this idea of convection currents as gears almost. But if you were going to have gears that were moving something, would you want the teeth of the gears to be made of rubber and or something even more ductile? And no, you wouldn't. And the asthenosphere is not, it's solid, but it's ductile. And so here's something ductile moving against something solid. It's not going to move the solid thing nearly as much as the solid thing actually just sinking.
Yeah. Yeah. Thank you. All right. Let's dig a little deeper. If an active silicate planet, one that when I say active, I mean it's convecting, its interior is convecting, as opposed to the moon and Mercury, where you don't have any convection. The surface is just pitted by impact craters. If an active silicate planet doesn't have plate tectonics, what is its tectonic style? And the answer is some kind of single lid tectonics. And it's like, what? What's single lid tectonics? Single lid tectonics contrasts with plate tectonics in that there is no global mosaic of moving rigid tectonic plates divided by weak boundaries, and there is no long-lived subduction that drives horizontal plate motions. And there's lots of different terms that people have used for what I call single lid tectonics, including volcanic heat pipe, squishy lid, and stagnant lid. I prefer to reserve the term stagnant lid for dead planets like Mercury and our moon, and single lid tectonics for bodies like Venus and Mars. So this is one of Clint's. Clint makes these incredible diagrams, which find themselves in my papers, but are also picked up by other people because it's like that really is nice. So here we got Venus, and Venus does not have anything that looks like a trench or a spreading ridge. It's got a lot of relief. It's got a lot of volcanoes. It's very active, but it has something like single lid. And that the term stagnant lid was the first term for the tectonics of Venus, which was applied in, after the Magellan missions had mapped its surface with radar. And, it was called stagnant lid. And, I don't like it because it's not stagnant. That thing is bubbling. All right. So my bottom line in this paper is that Earth had plate tectonics twice in the past 2.5 billion years. Here I'm using Clint's. Oh, look at that. I put his name there in the wrong place. Sorry, Clint. Go back to full screen. And, going back and forth between plate tectonics and single lid tectonics, we're clearly in plate tectonics today. And I would argue that it began sometime in the Neoproterozoic, but that there was an earlier episode between about 1.1 and to 2.1 billion years ago in the Paleoproterozoic when there was an earlier plate tectonic episode. And then the two are separated by a single lid episode in what's called the boring billion, but essentially is the Mesoproterozoic. You'll hear the word boring billion for the time from about 1.8 till about 800 million years. So 200 million years on either side of the Mesoproterozoic is the boring billion. And again, I'm not gonna venture into what Earth's tectonic regime was during the Archean. All right. Now the arguments that I've brought to bear are what I call plate tectonic indicators. So the most important ones are ophiolites. These are sites of demonstrable seafloor spreading, and And here we see the abundance of ophiolites through time. Lots of them in the Phanerozoic, quite a few in the Neoproterozoic, and a couple back here in that time. But I think there was an earlier episode of plate tectonics. That is an indicator of seafloor spreading, and more importantly, subduction initiation. And then there are subduction indicators like blue schists, which are glaucophane-bearing eclogites, metamorphic rocks, lawsonite-bearing metamorphic rocks, and jadetite, which is a form of jade. It's a gemstone. And these are related to subduction, which subduction is required for plate tectonics. So you can see that they're restricted, it's pretty much the same time span as ophiolites. And then there are collision indicators, the most important of which are called ultra-high pressure metamorphic rocks. These form when continental crust is subducted down to depths of 100 and 150 kilometers deep and then come back to the surface. They don't appear until about the same time in the late Neoproterozoic. And then there are gemstones, rubies and sapphires, that are associated with collision zones, and that's when they occur, although there's a couple way back here. Now, we can start looking at ore deposits, and this is something I did with Matt. So here's a distribution of porphyry copper deposits through time. They're disproportionately Phanerozoic things. There's a few at different ages, but it's reminiscent of the plate tectonic indicators, and it could be that some ore deposits are also containing this kind of information. So now a lot of people that say, well, Bob, you don't understand. There's erosion, and erosion removes things, and porphyry coppers being, shallow, mesozonal to epizonal mineralization systems, they're going to get eroded off because they typically happen in mountain belts, and so they're not reliable. And same thing with ophiolites. That's not so true with blue schists and lawsonite metamorphic rocks or ultra high pressure metamorphic rocks. Metamorphic rocks, if you erode, you just get more of them. So that's why you use multiple proxies for plate tectonics and the absence of plate tectonics. And then you can see these things are all missing from the Mesoproterozoic. Yeah, question.
Yeah, I'm sneezing.
Is there a question?
Yeah, I was wondering, first of all, a really cool diagram. But for the ophiolites, I was under the understanding that the oldest oceanic crust was only a couple 100 million years old. So I'm just curious, where are you finding these ophiolites? Or why would they be maintained?
What you were told is correct. The oldest in place oceanic crust is maybe 180 million years old. That's found off the east coast of the United States, maybe in the Gulf of Mexico, off the northwest corner of Africa, and in the far western Pacific. So that's in place oceanic crust. But ophiolites are fragments of oceanic lithosphere that have been thrust up on land. And in the past, the evolution of thinking about ophiolites has evolved quite a bit. In the beginning, they were thought to be, just normal mid-ocean ridge spreading crust that got thrust up on land. But as geochemists started working on them, they noticed that the geochemical signatures, especially the immobile trace elements, were very different than what you'd expect from spreading ridges and more consistent with convergent margins. And then we developed that a bit further by explaining this as a result of subduction initiation. That if you think about how a new subduction zone gets started, it's got to do with lithospheric collapse in the ocean, and then the upwelling of a asthenosphere over it, and then you produce spread oceanic crust in what becomes the forearc of a convergent plate margin, and that's in a perfect place to be abducted and thrust up on land when something comes in, and that's the origin of ophiolites. So thanks for expressing. The other people, I'm sure, were confused on that issue too. Okay, so now, any other clarifications desired on any of this blatant advertising? Okay. let's look at the distribution of ore deposits. So this is from Groves, who's one of the co-authors of the book, and he's looking at the ore types through time. So here's our VMS deposits. He's calling them VHMS deposits. Cypress type, Abitibi type, Kuroko type, doesn't matter. They're all, VH deposits. Then there's orogenic gold we talked about last time, paleoplacer and placer gold. Well, these two have to be related somehow, and you can see, in fact, they are. Porphyry copper, we just talked about. Porphyry molybdenum, related. Now, these are sediment-hosted uranium. That's going to be related to the oxygenation of the atmosphere. But you can see there's plenty of them in the Mesoproterozoic, as well as today. Then we've got the Karuna type, the Olympic Dam, the ilmenite anorthosite, the IOCGs, right? That thing that we get confused about. Is it a Karuna? Is it an IOCG? Is it an iron oxide apatite? We see this remarkable concentration in the Mesoproterozoic at a time when you don't see other kinds of ore deposits. And, that is very interesting. Now we get to the sediment hosted base metals, and here we've got some interaction with the exosphere, but the SEDEX zinc lead deposits are heavily concentrated in the Mesoproterozoic and also the Phanerozoic. The lead zinc Mississippi Valley type, they're mostly Phanerozoic. And then sediment hosted copper. I'm not sure what to do with that. So they acknowledge that there are some really interesting variations in ore deposits through time. And that really is very useful information for those of us interested in Earth's tectonic history. So fluids are the key to understanding the tectonic controls on mineral deposits. So we need to, we've talked about fluids, but let's talk about them again. So here we've got, fluid flow in the crust. So we've got to think about the pressure depth relationship, where, we got two pressure regimes to worry about. One is the hydrostatic pressure, which is more important when there's connected pore space. And then we got the lithostatic pressure, the weight of the overriding rocks. And so you can see that as burial goes on, the pressure regime in, these are presumably sedimentary rocks in a basin, are going to evolve from, hydrostatic PT regime to, approaching the lithostatic regime more. And that's sometimes called overpressure, the difference between the measured and the hydrostatic. But that's going to drive fluid flow. And in addition, in a basin, it's going to get hotter as you go down. The pressure following this curve is going to increase. And that combination of heating and pressure is going to drive out fluids. It's dewatering reactions at the base of a deep sedimentary basin. So, keep in mind that the geothermal gradient in the outer part of the Earth is on the order of 25 degrees per kilometer. If you have a sedimentary basin that's as thick as that beneath Houston, 10, let's just say it's 10 kilometers. That's probably an underestimate. But that's going to be 250 degrees there at the bottom, and that's well within the metamorphic green schist facies, and metamorphic reactions above all release water from minerals. And then, so that's one way of generating the fluids that can take part in mineralization. Another way is with tectonics. If you put a thrust fault, you're going to be squeezing rocks, and squeezing will also have a pressure effect and drive fluids out. And another way is, the fluids that come out of a magma. So as the magma cools, if it's a water-rich magma, then the water is going to be concentrated in whatever the remaining melt is. And as that melt crystallizes, then that fluid's going to develop an overpressure, and that's going to hydrofrac the surrounding rocks. We've seen good evidence of that with veins and things, and that will drive fluids too. And all of these can work together. right? You could have combinations of fluids being released in a given environment, tectonic environment. All right, so this is how fluids flow in the crust. So here's an orogenic belt. Let's say this is Denver, Mount Rocky Mountain's near Denver, and this is the Denver Basin, and fluids would get into that, and then follow their own paths. That's just sort of driven by gravity, and then there could be fluids coming up from either metamorphic reactions at depth or magmas, and then diffuse at depth, and then following channels, faults and things like that farther down. And then depending on the heat flow, if it's a uniform heat flow, you're going to set up some kind of a convective regime in the pore water if there is porosity, connected permeability. And if there's a heat anomaly, say an intrusion, you're going to set up a circulation around that. And on the other hand, if you have a salt dome, you're going to have perhaps opposite flow, as if that's a cold thing. All right, and we see these things over and over in the field. These are one of the things we enjoy seeing, but we know they're very common in mineralized system, and these indicate high fluid pressures that form them. So over there in the upper left is a subhorizontal quartz gold vein from the Donalda gold deposit in Quebec. Have you heard of that one, Matt? And then next to it is Madison, you have a question?
No, I have not heard of that one.
Okay. Yeah, I mean, anything Canadian, the questions are going to go to you, right? Madison, did you have a question?
I do, but it's going back a little bit.
That's fine. That's fine.
Kind of basic. You were talking about how for every kilometer down you go, the temperature increases like 25 C.
Yes.
This is a weird hypothetical. So if you were to pile up like a kilometer's worth of sediment or rocks on top of a spot, is that just due to heat diffusion and then it's lost to the atmosphere? Or is there something more going on there? So like if I added a kilometer, would the temperature go up by 25 degrees, or is it only if you're getting closer to
Okay,
the
so
core?
we're talking about thermal equilibrium, but at thermal equilibrium, that big pile has been there for a long time, then it's going to be, its temperature regime will be controlled by conductive flow from the lithosphere. So remember, the lithosphere is where heat is transported by conduction, and the asthenosphere is and the deeper mantle is where it's transported by convection, right? So in the asthenosphere and deeper, we follow an adiabatic gradient, which is less than a degree per kilometer. But in the lithosphere, including the crust, we're following a conductive geotherm, which is much steeper. And it's set overall by the fact that the base of the lithosphere is at about 1200 degrees centigrade. So, 100 kilometers down, it's 1200 degrees. And we know at the surface it's not 1200 degrees, or else there'd be lava flows. So that temperature gradient, you're just dividing 1200 degrees by however thick it is. Now, if you do that, 100 kilometers, 1200 degrees, okay, then you come up with 12 degrees, but the conductive regime gets a little steeper near the surface, but it's following a conductive geothermal gradient, and we can talk about the different parts of the Earth having different conductive geothermal gradients. Areas where there's a lot of magmatism, you're going to see much higher gradients. Areas like places where you have subduction zones, you're going to have a lower geothermal gradient because it's cold at depth. But that's basically what's going on. Does that answer your question?
Yeah. And then you might be about to cover this, but when you talk about kind of switching between these tectonic regimes, how are you picturing either them kind of coming back together into this single lid or being broken up into this mosaic of plates?
Oh, okay. That's a good question. I think that is actually gets at the heart of the controversy, right? if the idea has any merit, then it's worth exploring further. So one way to make a single lid from a plate tectonic episode is to have let's imagine a world with two supercontinents, and all of the plate tectonics is going on between them, and then they come together and collide, and no new subduction zones form. That's one way, and I think that is a good explanation for what happened about 1.8 billion years ago when the supercontinent, I think it's called Columbia or Nuna, formed, and that's sort of terminated the Paleoproterozoic plate tectonic in my episode. Now, creating a plate tectonic regime out of a single lid regime, that requires, the formation of a subduction zone, and that subduction zone infects the surrounding areas. So the oceanic lithosphere has to be overly dense, and there have to be weaknesses where it can fail. But that will take a long time. And in fact, if you just think about sort of plate tectonic rates, for these activities of, the fastest plate is on the order of 200 millimeters per year. If you imagine that you could propagate a subduction zone, a convergent plate margin at 200 millimeters per year, it would take on the order of 200 million years to make a global mosaic from a single subduction zone. So in the one case, it might be possible to move very quickly between plate tectonics and single lid, but it almost certainly takes a lot longer to go from single lid to plate tectonics. But area for research. Love those. Okay, so these are all different demonstrations of the role of fluids, and some of these are in ore deposits and some of them are not. But once you get away from calling them dikes and veins and thinking about what they were originally, you're looking at hydrofracking by nature. Hydrofracking gets a bad rap because oil companies do it, but the reality is it's pretty common in nature as well. We just don't call it that very much. And with the water that they use for actual industrial hydrofracking is, number one, a lot cooler and a lot purer, even though they put stuff in there, than these systems are going to be at hundreds of degrees centigrade, and they're going to be chock-a-block full with everything, of which water may be the least important part. But that's what's going on here, right? All right, but what is the ultimate source of mineralizing fluids? And here is definitely one of the important players. So here we have a subduction zone, and oceanic lithosphere sits on the bottom of the ocean for a long time, and it soaks up a lot of water and cracks and mineral reactions, and then you even start to serpentinize the underlying mantle lithosphere. These faults that happen as the plate begins to bend will let lots of water get into the mantle and serpentinize it. The geophysicists are showing us examples of lowered seismic velocities here as a result of serpentinization. But as this material goes down, it gets squeezed and heated and starts to lose water. So that water and other stuff comes out of it. And we know that's responsible for generating magmas beneath island arcs. That's pretty settled science. So that's definitely a major source of water and sodium, chlorine, salinity, metals, but it's not the only source. So let's look at some features of mineralizing fluids that come from depth. So we're not talking about surface fluids. So we're not talking about brines or the fluids that are involved with weathering, or the fluids that transport placers. Now, the magmatic ones, they are not really associated with fluids unless you consider magma to be a fluid. We're talking about things like, sediment hosted ore deposits, definitely hydrothermal. Although there we get a mixture between surface waters and magmatic waters, so it's a little complicated. And then these metamorphic deposits where you're squeezing the water out as a result of metamorphosing rocks. So these are really the endogenic ones, and it's not as clear as we might like them to be. There's, if I assert that sediment hosted ore deposits are good capture endogenic fluids, somebody could reasonably say, well, wait a minute, there's a lot of surface waters and groundwaters involved with that too. So the point is it's complicated, but it's interesting. All right, so this gets us back to these fluid inclusions because they are the one thing that have the chance to capture the fluid that was responsible. And Matt's pointed out that these are not altogether reliable, that they only capture one stage in the evolution of the fluid, but nevertheless, this is what we've got. So we can study these to understand the salinity of this fluid originally and its homogenization temperature, right? When it was captured, these little crystals and things were not in it. This all separated and formed as the fluid inclusion, as the host rock and its fluid inclusion cooled. So you basically heat it up and you get what's called the homogenization temperature, which is kind of a minimum of the fluid, right? Because if the fluid's going to be homogenized at 400 degrees, that doesn't mean it couldn't have been originally 600 degrees, right? You just know that it had to be at least 400 degrees. All right, so let's look at some fluids. And this is from a paper by Bodner, who basically compiled all of this data. These are Mississippi Valley type ore bodies. And this is the distribution of salinity. Most of these are going to be salinity, and we'll see several of these, versus homogenization temperature. And then here we've got some nice statistics on the homogenization temperature and here on the salinity. It's a huge range, but it looks to me like 100 to 200 degrees centigrade and 20 to 25% salinity for the most part, right? So these are not real hot ore deposits. I mean, they would burn us, but as ore deposit fluids go, they're not very hot. So here's a VMS fluid. Now this one, volcanogenic massive sulfides. And one of the things you see is the huge spectrum. They're also separating the fluids in VMSs according to whether these are felsic hosted or mafic hosted. Mafic hosted seem to be don't have the range and salinity, or for that matter, the temperature that the felsic hosted ones have. But if you had to say, okay, it's basically seawater. The salinity is about seawater. There's some cases it's higher, but for the most part, it's what you'd expect from a seafloor hydrothermal vent. It's recirculating seawater, and it looks like that for the most part is true. And then the temperatures, they quite different than the Mississippi Valley type. These go up to 400 degrees. We could say 150 to 300 is kind of normal. And Matt, you know more about these deposits than I do, so just chime in anytime.
Sure will, but you got it so far.
Thank you. All right, now these are epithermal deposits. We talked about epithermal deposits previously, and you can see, the salinity is quite low, but the temperature is on the order of 200 to 300 degrees. And here are the precious metal deposits. I'm not sure, we went over quite a few. We talked about what precious metals. I'm assuming this is all gold. And then, I'm guessing these are, orogenic gold and other kinds of that related gold. And you can see that's also got very low salinity and temperatures that are not, go between, what is that, looks like 200, 250 degrees, something like that. And then remember, we have the low sulfidation epithermal, the intermediate sulfidation epithermal, and the high sulfidation, right? Which are sort of paying attention to whether it's close to the underlying magma system or farther away. And you can see that the high sulfid, they kind of overlap, except the intermediate sulfidation seems to have some higher salinities. You know, the high sulfidations have very low salinities for the most part. It's kind of interesting. He's broken it out between base metals and precious metals. Okay. These are pretty complex diagram. Porphyry coppers are very interesting because you see this bimodal distribution in salinity. So the temperatures on the order, you know, we could say 200 to 400, but the salinities break into two major groups, which is very interesting. You know, one of them is relatively low salinity, not as low as any of the things we've been looking at, but the other one is very high salinity. So when you see fluid inclusions with two different salinities in a single deposit, you're thinking of phase separation. So phase separation is as you cool a fluid, it can separate into two end members, essentially become an immiscible liquid. And it's kind of interesting because we've talked about immiscible liquids as being the presence of polar versus non-polar components. But here, something else is going on that I don't understand, and maybe Matt can illuminate us.
Well, so the phase separation is essentially boiling, right? So you get a vapor phase, and so you preferentially removing water, and so the residual phase becomes much more saline, and then the vapor phase will recondense as it cools and form a less saline fluid.
Okay, so the low salinity fluids are the boiled remnants, and the unboiled is the
Yeah, and then superimposed on that, you've got the interaction between magmatic waters and meteoric waters circulating and interacting with each other. So
okay, maybe that's the low salinity. Yeah, it's complicated, but it is interesting. This clear two groups of fluid inclusions in porphyry coppers. And you see the same thing in porphyry mollies, you know, they're, you know, again, same kind of system. Tin tungsten porphyries, they're less clear, but it would appear that you've got the same thing going on. And then skarn deposits. Now remember, skarns are just deposits that form on the edge of plutons. And so the salinity and the temperatures are quite a wide range. You know, temperatures, you know, ranging from about 100 to 600 degrees, and salinity going up to very high values. And that's because, you know, the magmas that come in are going to have a very wide range of temperatures, and you know, they're interacting with pore fluids that can also vary a lot depending on the depth and the host sediment. Now, Carlin type deposit fluids are mysterious Carlin type deposits. They are low salinity, right? None of these are more than 10 weight percent sodium chloride, but a huge range in temperature from 100 to 300. But you know, these look kind of epithermal, right? Because they're sort of low temperature, low salinity kinds of things. Orogenic gold, yes, Madison.
When we're talking about salinity here, is it exclusively NaCl or any kind of salts? And do we know if there's a difference in sort of the ionic charge or their effect on the water activity?
Okay, I'm going to take a whack at it, and then Matt will correct me. So that is a salt crystal, right? NaCl. It could have some potassium in it, but for the most part, anything that is crystallized in a fluid inclusion is, and that has this shape is thought to be salt. Isn't that true, Matt?
Yeah, for the most part. I mean, normally salinities are expressed as NaCl equivalent in weight percent. So yes, you can have other things like calcium and potassium and magnesium chlorides and so forth, and you can have a small amount of sulfur or in some cases, a large amount of sulfur because you can get sulfide inclusions in fluid inclusions, for example. But yeah, it's usually expressed as an equivalent NaCl.
Okay, thanks. So it could be other things, but it's some kind of a very ionic crystal.
Yes. Yes.
Now, orogenic gold, for the most part, is fairly low salinity. Remember, these are relatively deep. These are from metamorphic, thought to be from metamorphic dewatering of metamorphic rocks and somehow carrying gold. Relatively low salinity and wide range in temperatures from 100 to 350 or so. Now, this is an interesting diagram. These are the composition of fluid inclusions in orogenic gold deposits. And now we're looking at sodium chloride, and I guess equivalents, CO2 and H2O. And this is the spectrum of these fluids. Not so much CO2 in that fluid. So I just pulled this stuff from Bodner and sort of summarized it, ore deposit types, MVT, VMS, epithermal, Carlin gold, orogenic gold, porphyry copper, porphyry moly, skarn. So the temperature range, that's sort of what I've eyeballed. And then the salinities, and then whether or not it's bimodal salinity on there. I was just trying to organize a huge amount of data. No, so because of these different fluids, the endogenic mineral systems will differ depending on plate tectonics versus singlet. So this plate tectonics, the one thing it's going to do is deliver a lot of water into this hot region, and it'll cause melting, and it'll do lots of things. We have studied what subduction zone processes a lot. We've studied what goes on with respect to mineralizing systems in subduction zones a lot less. That's kind of a wide open field. But you can see that there's a lot more water going into the earth, into this system, than there is in a single lid tectonic regime. So we predict that there's going to be a lot more water rich. There's going to be a difference in the ore deposit types between single lid and plate tectonics, just because the fluids are going to be different, right? Single lid, there is some water that they can bring in, right? These guys, these drips can bring in water. And just because this is identified simple-mindedly as single lid doesn't mean there's no subduction zones. There could be scattered subduction zones, and those would deliver water in the same way, but it's not going to have, the tens of thousands of kilometers of subduction zones that plate tectonics have, right? Single lid, those fluids are not going to have as much water in them as plate tectonics, when you're going to have lots of water in the mineralizing system that's responsible for endogenic deposits. Ask anybody if they noticed anything missing from this list. Anybody notice any important endogenic ore deposits missing from this list? Yes, Matt.
IOCG.
Yeah, the Karunas, all of the things that we think are important in the Mesoproterozoic are not here. Now, maybe Matt could answer your question. Why aren't they on there?
Well, Bodner was 2014. So IOCG wasn't that long before then that IOCGs were really classed as a
Yeah.
as a separate type of ore deposit. I forget what year that really was, but it wasn't that long ago. And that may have something to do with it. So that's the only thing I can think of.
Yeah, or it could be that they don't have any fluid inclusions. That's a possibility. You're saying, well, that's probably not what happened, but the
Whenever you got
interesting
quartz
thing is
around,
it would be nice
yeah.
to include fluid inclusions from Mesoproterozoic characteristic endogenics in this list, because that would test the suggestion,
Exactly.
that,
Yeah.
but,
Yeah.
but something, there's a little bit of research needs to be done. All right. Now, so then they go on to section 9.2, evolution of the early Earth and the earliest metallic mineral systems. So mineral, and we've commented that cratons are particularly good places to have if you're interested in ore deposits. And it should be no surprise that Canada, which has a huge craton, and Australia, which has a huge craton, and South Africa which has a huge craton, are all very important mineral producing areas. What's interesting is that China, it has a craton, but its mineralization is not really as concentrated on as cratons, and they're not very big cratons. So China's kind of the interesting exception to the overall impression that I get, and I think, Matt, you probably would agree with me, that in general, Archean cratons are better places to look for ore deposits than non-Archean cratons. Is that a
Yeah,
fair?
except maybe VMS. Well, I guess it really depends on the deposit type, right? So porphyry copper, no. VMS, well, VMS you can find almost anywhere. But yeah, it really depends on the deposit type.
Yeah. All right. So anyway, some 3 billion-year-old cratons are enriched in siderophile elements like nickel, chrome, and PGE. Although I'm not sure chrome was siderophile. Wonder why I said that. Archean cratons are enriched in tin, tungsten, uranium, and thorium. And why their old continents, old cratons are so rich is unknown and worthy of research. So right now we've only got a pretty small area of the Earth is covered by Archean cratons, but so the parts that have been returned to the mantle, they recycled their mineral inventories back into the mantle. All right, so DeWitt and Thiart identified 6 selected metal groups to look at the relationship between mineralization on the craton versus next to the craton. And they looked at 11 cratons. They ignored India and Russia and the, North Scandinavian craton and some other ones, obvious ones to go after, but this is a pretty good sampling. So those are the ones they looked at. And these are the way they broke out the groups. So gold obviously deserves its own group. Chromium, nickel, PGEs, and titanium are second group. Copper, zinc, lead, barium, those are related. Tin, antimony, tungsten, uranium, thorium, rare earths, right? These are the number of mineral deposits they had 20 years ago, divided into 6 groups. And their abundance on each of the cratons. And then they compared it with on the craton and younger. So that's Africa on the craton versus Africa younger. South America on the craton, South America younger. Australia on the craton, Australia younger. There's gold, in every case, gold is relatively more abundant on the craton than off the craton. Chrome, nickel, platinum group elements, same. copper, lead, zinc, barium, pretty much the same. Tin, antimony, with the exception of Australia, where it doesn't seem to be much difference, they're the same. Tungsten, it doesn't work for tungsten in South America, and it doesn't look like there's any in Australia. Uranium, thorium, rare earths, it doesn't seem to work. So that's the total. They put them all together, on the craton, off the craton, on the craton, off the craton, on the craton, off the craton. So it seems from that statistical treatment, and I'm sure a serious statistician would take exception, but it certainly doesn't damage our perception that cratons are metallogenically more favorable than adjacent regions. So if that's true, then why are there more Archean mineral deposits than in later times? So part of the answer could be that Earth's interior was hotter, so it was easier to melt the sulfides in the mantle and extract metals, right? You have to, their metals are held in the mantle in some kind of a sulfide phase. Matt, you'll correct me if I'm wrong. And so if you can melt that sulfide phase, break it down, then those metals will travel with the magma, where they'll be easier to remobilize into ore deposits. They suggested possible mantle overturn events, bringing material from deep in the mantle upwards. That's implying that the deeper mantle is more enriched in metals than the shallower mantle. And then this was close on the time when, Earth was still being intensely bombarded by meteorites, and meteorites carry a lot of metals with them. So if those were remobilized after impact, that could contribute to the inventory. So those are just some of the ideas. Then they get into the supercontinent cycle, which they figure very prominently in their treatment. So just to remind you what the supercontinent cycle is, this is the periodic coming together and breaking apart of continents. They talk about this in tectonics. So there's the supercontinent Pangea, and then there's one supercontinent and one ocean. And forget this stuff. This has got to do with sea level, and we're not too worried about sea level in this class. So it breaks up, and then you create a new ocean in there, and then it comes back together. So from one supercontinent to another supercontinent, that's a supercontinent cycle. And it's, the time scale for a supercontinent cycle is on the order of 300 million years, but it's quite flexible. So this is another nice figure that Clint made, which shows the supercontinent cycle. It actually is showing the Wilson cycle, which is the oceanic equivalent of the supercontinent cycle, right? The Wilson cycle is the opening and closing of oceans. The supercontinent cycle is the disaggregation and coming together of continental fragments. The two operate together. So here you're seeing, continental rifting. Oops, go back. The formation of a passive continental margin. There's another one on the other side over here somewhere. Then you have to start a new subduction zone. And then you go into normal subduction, which closes the ocean, brings them back together. That is, sort of a orogenic belt. And then the orogenic belt will relax and form a continental rift, and the cycle starts over again. That's the way we look at it. So if we look at these, the supercontinent cycle and the Wilson cycle, we're going, well, how would ore deposits respond to that? And the book doesn't really explore that very well. Obviously, this tectonic setting is going to have more material recycled from the subducted slab, but how do we assign likely mineralization scenarios to these two, the supercontinent cycle and the Wilson cycle? And they focus very much on the supercontinent cycle without being very clear about why ore deposits should be sensitive to that. So here's the last supercontinent. This is Pangea 300 million years ago. You know, that's Pangea. Here, the Pacific is the biggest ocean in the world. It's never been smaller than it is today. It used to be called Panthalassa, and then a reentrant of Panthalassa is the Tethys. So Muller et al. Identified 5 supercontinents, and then this is my guesstimate for what percentage of geologists agree that their supercontinent existed. Pangea, more than 90%. I mean, pretty much any non-insane geologist understands the evidence for Pangea. Gondwana, that was the previous one at the end of the Neoproterozoic. I'd say about 80% of the community accepts that. Rodinia, okay, maybe 70%, maybe more. Columbia, which is the 1.8, sometimes called Nuna, okay, maybe 60%. Kenoraland at 2.7, maybe I would say less than 50%. And then Ur at 3 billion years, maybe 30%. Now, this, science is not a democracy, but you can see the areas of controversy relatively easily in this, that when they identify the Pangea supercontinent, we have no problem accepting that as a useful statement. When they identify Ur supercontinent, we should view that with some skepticism. Any questions on that? It's hard to find out what scientists think, because for a number of reasons, but so sometimes you just have to take your best guess. All right, so they start showing these things. So here we've got a plot of porphyry copper gold, VMS deposits, and orogenic gold. And we're seeing, there are 5 supercontinents. And I would draw your attention to the Columbia Rodinia supercontinent. It's like, wow, if there wasn't that little white area in there, you'd think it was a single supercontinent, which is consistent with a single lid tectonic regime. But, this is what it looks like. And you're going, okay, what do we do with that diagram? I mean, they're obviously guiding us to their opinion, but I'd like to know what you guys think. Do you guys see a signal in this where the supercontinent cycle controls certain types of ore deposits? Does anybody have an opinion? Is
Do they-
anybody? Go ahead.
Well, I was just going to ask that. So that little thin white line between Columbia and Rodinia, do they describe the evidence for that? Because
No.
that implies an ocean, right? Or that implies complete breakup and then a reassembly.
And that would imply things like ophiolites and passive margins and things
Yeah.
like that are not observed.
Right.
So no, they're sometimes things are said in science that are, what's the right word for it? Accepted wisdom. And the supercontinent cycles and its role on ore deposits is treated as accepted wisdom in this book. And I don't think that's useful unless they would work harder to explain how the supercontinent cycle would cause different kinds of ore deposits to form at different times. Right? Okay. Who's got their hand up? Andrew.
I just had a quick question about iridium. Do they look at iridium values during this? Because I'm assuming that it would be different if iridium is like falling on land versus into the ocean and then maybe like getting subducted somewhere. So I was just wondering if there was like, you could look at that to trace supercontinent cycles somehow.
Well, there's so little iridium in any kind of a surface rock, including igneous rocks. That's why it was such a useful tool for identifying meteorite impacts. Iridium is a serious siderophile element. So we're incredibly depleted in iridium. It's one of the reasons why it's so expensive. It'd be even more expensive if there were more good uses for it. But you know, you don't see any evidence of that. It would be interesting to see if modern arc igneous rocks had an iridium signal over those that are not subduction related. I have not seen that study, but that's certainly, you know, you're formulating a hypothesis. And as you know, the more beer we get in us, the more hypotheses we come up with. And then the beer wears off and we're going, okay, where do I want to spend some time? Because it's not fun proving yourself wrong. It's a lot more fun doing some work and going, huh, maybe I'm right. Right. And then the fun begins of trying to convince other people of your ideas. But thanks
Thank
for that
you.
question. All right. So we do think that because of the differing fluid compositions, any mineral deposit will differ depending on whether it's plate tectonic versus single lid tectonic regime. So we've explored these reasons, and but the world of mineralization hasn't really looked at it this way because these guys that do ore deposits, they're experts in ore deposits, and they look to the people that do tectonics to give them the tectonic information. Just like I, you know, consider myself an expert in tectonics, and I look to the ore deposit people to give me that information. I sort of treat what they give me as, what did I say, accepted wisdom. And so this supercontinent cycle story has deeply permeated our science, and it's for you and other young people to decide how useful it is, at least in this particular instance. I think you can get a sense of how I feel about it. But let's keep digging into it because this was in the book, right? Now let's look at let's go look at IOCG deposits from their book. So here is the age. So this is IOCG deposits, and then iron phosphorus deposits. These are, you know, sort of related to IOCGs, Karunas. I mean, these things are, the terminology is so much in flux that I'm confused. Do you want to elucidate any further on that statement, Matt?
No, I think confusion is probably a good default position on this one.
But you can see that there's some major ore bodies, just not the things that we were looking at before, right? Gold, VMS deposits, orogenic gold, porphyry coppers, those things. I have no problem relating those plate tectonics, although VMSs could also be single lid. But porphyry copper gold and orogenic gold, I have no problem assigning those to plate tectonics because we've seen their fluid inclusions are water rich. So how else are they going to get it? But these guys, you know, it's not like the Mesoproterozoic is barren. In fact, your book talks about the Mesoproterozoic as being kind of a mineral bonanza, but it's a different kind of mineral associations at that time. Here you can see, you know, Olympic Dam, one of the biggest and most enigmatic of ore deposits, you know, smack dab in the Mesoproterozoic. The MT copper, do you know what MT copper is, Matt? I'm not sure I do. Oh, megatons.
Megatons, yeah.
Yeah. Okay, there's plenty of that in Mesoproterozoic, but it's associated with IOCGs. And then the iron phosphorus, you know, it's there too. I'm guessing, but I don't have any data to support my hypothesis that these are water poor systems. That the fluids, if there are fluid inclusions in them, they're maybe CO2 dominated. I don't know what they would be, but I think they're probably water poor. And if anybody knows anything about fluid inclusions in these kinds of deposits, I would love to hear about it.
I can put a review paper in the chat.
Oh, there is one. Okay, good. Thanks. Okay, so here we've got the this is their plate, their supercontinent assembly, Ur breakup, Kenora land. I guess it broke up somewhere in here, Columbia, which happened right at the beginning of this, what I think is a single lid episode, and then this long-lived subduction orogeny along its margins. I don't know where that comes from because there's nothing that looks like subduction along its margins in terms of plate tectonic indicators or ore deposits. Rodinia, breakup assembly, Gondwana, Pangea is still breaking up. So do you see what they're seeing with the supercontinent cycle and ore deposits? Or am I the only one that's going, why are they doing this? It makes no sense. Something to think about. All right. Yes, Clint. Yes, Clint.
Sorry. When I took Kent Condi's evolution of the Earth, or evolution of the Earth, he talked about the same kinds of thing, and it described like the types of ore bodies that form in different tectonic environments today. And are you using any of his data in this, and which I'm sure has evolved over time?
No.
This is Santosh and Gross, but anyway.
Yeah.
Anyway,
So,
it's one of his things of interest. So go on.
Now, Kent and I get along well. He thinks I'm insane for thinking that plate tectonics hasn't operated all through this time. That's the nature of science, is if you're in an interesting area, you're going to have disagreements. And some scientists, they will go into an area to avoid disagreements. Now, you can understand why that might be. Say you're a young professor, you're trying to get tenure, and some of your people on your committees have strong opinions. So you might want to avoid disagreeing with them. But anyway, the point is, if you're doing interesting science, you better be prepared to disagree agreeably with people. Let's put it that way. All right. So this paper in 2020 I wrote, I in the previous work I worked on, okay, what are the plate tectonic indicators? And it was like, well, if you're gonna talk about single lid, then you have to come up with single lid indicators. So it's like, okay, these are the ones I came up with. So these are A-type granites. We've talked about them several times. They're relatively anhydrous as opposed to I-type granites. And there's a real peak of them in the Mesoproterozoic. I mean, there's some still today, but there's a real peak in the Mesoproterozoic. So I call that dry magma indicator 1. And a second one is anorthosites. So anorthosites are very unusual rocks. These are huge massifs dominated by plagioclase. They're magmatic. And how they form is very problematic. But the best explanation for them is that when you get an iron-rich magma, plagioclase will float. So if you allow a normal basalt to fractionate extensively without crystallizing magnetite, that is relatively low oxygen fugacity, it will get more and more iron rich. It will get denser and denser, and eventually plagioclase, instead of sinking to the bottom of a magma chamber, will rise to the top. So that requires, in that interpretation, anorthosites form when you have very iron-rich magmas, and very iron-rich magmas are known to evolve in low oxygen fugacity environments, which are associated with dry magma systems. So for that reason, contorted reason, I call these anorthosites dry magma indicator number 2. Now, the thermobarometric ratio is basically you can study a metamorphic terrain and use mineral equilibrium to get temperatures and pressures. And Mike Brown and others at the University of Maryland have done this, compiled this data for the metamorphic terrains of all ages around the Earth. And they found that it's not very clear here, but that the Earth, the TP of metamorphic rocks, which are always crustal rocks, right? They are the highest in the Mesoproterozoic. And if you think about what's going on with single lid, plate tectonics cools the mantle in 2 ways. Number one, where the asthenosphere is coming up at mid-ocean ridges, that's taking hot material and exposing it to cold seawater. And then in subduction zones, you're taking cold lithosphere and injecting it into the deep mantle. That's going to cool it too. So when you have a single lid, you have neither of those things. So you're going to basically insulate the interior of the Earth, and potentially heat will increase, and you'll get a higher T/P ratio, which is what we see for the Mesoproterozoic. And then finally, by the way, these are not my compilations. I just took these from the literature. There is the distribution of passive margins through time. And this is by a guy by the name of Dwight Bradley. And there are ones that he's more confident with and less confident with. So they're very confident about modern passive margin sequences, but as you go back in time, the confidence decreases. There is significant amount of passive margins forming in this earlier plate tectonic episode, as you'd expect, but there's almost none in the Mesoproterozoic in the boring billion. So these 4 indicators, which I call plate tectonic single lid indicators, coupled with the absence of plate tectonic indicators this time, to me is very convincing evidence that we're dealing with a single lid episode. And mineral deposits should also be sensitive to dry versus wet magmatic environments. Okay, so let's see what the Mesoproterozoic looks like in terms of ore deposits. So this is from Groves 2010, Charlier et al. These are some Mesoproterozoic magmatic ore deposits, which are consistent with a single lid episode. There's the Karunas, dominantly there. There's the iron oxide gold, copper gold. They found some in the Phanerozoic in South America. And then there's ilmenite and orthosite. These are all very common in the Mesoproterozoic, and orogenic gold and porphyry copper. If you tell someone you're looking for porphyry coppers in the Mesoproterozoic, they'll look at you like you've lost your mind. So there's some really major differences in mineralization cycles of these endogenic systems through time that is not captured at all by the supercontinent cycles of Muller. So, if I'm going to criticize their model, which is based on, the supercontinent cycle is controlling ore deposits through time, then it's not enough just to criticize them. I've got to give you something to replace that, right? That's this. All right, and then kimberlites are another thing. That's fluid pressures drives kimberlite explosions. So you get, kimberlites are these things that are basically, incredible single eruptions of very fluid dominated material from the base of the lithosphere, and sometimes they bring up diamonds. So there's a community that's extremely interested in them. as you know, even in Canada, used to be Canada didn't have diamonds. Now they got lots of them. You know, they started finding these kimberlite diatremes up in the Northwest Territories. Now, if you look at the distribution of kimberlites through time, you know, this is something Matt and I and some other people worked on. They are dominantly young, right? So this is Archean, Paleoproterozoic, Mesoproterozoic, Neoproterozoic. You know, they do occur back in time, but remember these are vertical intrusions that go from the base of the lithosphere all the way to the surface. So erosion, yeah, maybe these will narrow as they go down, but believe me, if you're looking for diamonds and there's a diamond bearing kimberlite pipe, you're gonna want to find it. So these guys are looking for these things. They're not paying too much attention to what we think about the tectonic evolution of the Earth. They're just, you know, doing stream sampling and looking for indicator minerals and things like that. So one of the ways to interpret this is what we're seeing is a huge increase in the amount of fluids that's being delivered to the base of the lithosphere as a result of subduction. So here we've got, you know, a single lid tectonic regime. You know, there's the graphite diamond stability field, and there's really not that much fluid being pumped into the mantle to cause these, you know, kimberlite eruptions. But here, you know, with the subduction zone, we're still figuring out how long it takes to release all the water from a subducted slab. And it seems to be pretty continuous. It's less and less with depth, but still, you know, it's going to accumulate somewhere down in the lithosphere. So you're going to build up this, you know, fluid pressure at the base of the lithosphere that allows something like this to happen, right? And there just wasn't that kind of fluid pressure. Well, it's not, you know, supercritical fluid pressure at the base of the lithosphere. Easy to make kimberlites in the last few 100 million years. All right. Now, the book also talks about preservation, that preservation is important because only those mineral systems that are preserved can be found and exploited. So the book says the mineral systems that are most likely to be preserved are those that form in continental basins with thick subcontinental mantle lithosphere or subcontinental lithospheric mantle that is buoyant because of its density. So that may be something like the Athabasca Basin. Those that form at deeper crustal levels, right? So erosion will not remove those. And those that are preserved due to rapid burial by thick sedimentary sequences in rift basins. And in contrast, those that are eroded from actively uplifting volcanic arcs or ephemeral rift zones are less likely to be preserved. So this simple-minded hypothesis suggests that hypozonal deposits would be more common in the Archean and epizomal deposits would be more common in the Phanerozoic. Are they? So, Matt, do you have any comments on that interpretation of what they said?
No, I think that's a reasonable hypothesis. I'm curious to see what the rest of the lecture is going to say about that.
All right. So does anybody have an opinion about this figure? Let's take a minute or two to look at it. So we're looking at genetic types, sedimentary, basin, hydrothermal, defoliatization, hydrothermal, volcanic hydrothermal, magmatic, hydrothermal, magmatic. So this is a different way to break out ore deposits, but that's fine. We know what they're saying. Then here's the mineral systems, paleoplacers, basinal hydrothermal, you know, MVTs, SEDEX, BHT, Broken Hill type, I guess.
Broken Hill type. Yeah.
Yeah. Okay. Orogenic gold, VMS, copper, zinc, lead, gold, porphyry, skarn, copper, gold, Kiruna type, iron, phosphorus, IOCG. It's funny they put them in the same group. IRGS, intrusion-related gold systems. Yes. And then the magmatic, the komatiite, nickel copper, mantle intrusion, nickel copper, PGE, layered intrusion, PGE chrome, spodumene, lithium pegmatite. Interesting, they wouldn't call that hydrothermal, but okay. Carbonatite, rare earth, niobium, copper. Okay, so, and then here are the supercontinents, right? Again, now the gap between Columbia and Rodinia has expanded. But does anybody have an opinion about this graph? What? So the title, the caption is Temporal Distribution of Metallic Mineral Systems Primarily Controlled by the Supercontinent Cycle, including the boring billion. Systems arranged in order of genetic types. Yes, we see that. What do you see the strong control of the supercontinent cycle on these deposits?
If I can make a comment,
Oh, absolutely.
I would like it to have been ordered in like with like, so that you could see, rather than by deposit type, those that are common in the Phanerozoic and Paleoproterozoic, and then those that are common in the boring billion. If they were all lumped together, it'd be easier to visualize what's going on.
Well, but remember, that's definitely not their underlying
Sure.
hypothesis.
That's
Their
true.
underlying hypothesis is it's a supercontinent cycle that's controlling everything. Because
I find this, yeah, no, that's fair. This diagram's really hard to see though, or to really follow.
well, I would say this diagram's really hard to agree with because if they pulled out the supercontinents and said, let's lump and let's organize these deposits, on the left in a rational way, and then see what the common elements are in terms of temporal distribution. I think this diagram could be improved, but I think this diagram more than anything else is showing us how confused this very complicated and important field is. Each of the people, the practitioners, let's say a VMS copper, zinc, gold, lead person, they know their stuff. They know the other things, but an IOCG person, they're different. And this I think this figure is sort of representative of the confused nature of the science, is the way I would put it. And that's not to criticize anybody. It's just to help you deal with what I imagine is your confusion about some of these diagrams. Does anybody agree with that statement or find it intellectually offensive, what I just said? They're so shy. I don't blame them. All right. Then they go on to the temporal evolution of metallic mineral systems. So they say that the events in Earth history affected the distribution of metallic mineral deposits. These, and they list 4 of them, and the supercontinent cycle, they've made that abundantly clear. The boring billion within that cycle, sometimes they seem to waffle and go, well, it's all plate tectonics, but then there's something else going on in the boring billion. And then there's the Paleoproterozoic great oxygenation event, which is going to have a huge effect, as we've seen repeatedly for the exogenic ore deposits, and the Neoproterozoic oxidation event, sometimes called the NOE, and the associated Cambrian explosion of life. And life starts to play a big role in sort of the evolution of ore deposits. So let's take these one by one, and metallic mineral systems that have a fundamental connection to the supercontinent cycle. And the most common mineral systems in modern subduction-related convergent margins are porphyry, copper, gold, moly, epithermal, gold, silver, VMS, copper, zinc, lead, gold, and orogenic gold systems. Matt, do you think VMS belong in there, or could they form in a non-plate tectonic environment?
That's a great question. I would still put it in there, and You know, most of the ones that would be preserved in the rock record are going to be subduction associated. So yeah.
Okay. And then they say, well, within these groups, the epithermal systems that form at very high crustal levels and rapidly uplifting arcs are going to be the only ones we're going to have left are going to be young. And these largely post-date the breakup of Gondwana and Pangaea. That's neither here nor there because it's just, you know, elevated regions are going to get eroded regardless of the tectonic regime or supercontinent cycle. And porphyry, skarn, copper, gold, moly systems form at slightly different crustal levels in the same arc systems. This is interesting. So now they're relating some of the epithermal ore deposits to porphyry coppers at depth, which I don't know if that's established. It's certainly an intriguing suggestion. Do you know, Matt?
Well, there is a depth relationship, and I was just about to go check because from memory, and I could be wrong, but I think that porphyry moly systems, you know, molybdenum dominated, are deeper than porphyry copper. But I'm going to check that.
But in general, you know, the idea that these epithermal systems, in some cases, are underlain by porphyry deposits at not too great of a depth wouldn't offend you terribly.
No, and in fact, I've got a colleague who was just in Mexico working on a property which is an epithermal system, and they're trying to come up with ways to then vector to what they hope would be a porphyry copper system underneath, or at least related.
Now that's really quite interesting as we think about how can we get more of some of these elements is if we can link these systems, you know, if we find an epithermal and indeed there is a porphyry copper underneath many epithermals, then it's like, okay, we got a very useful exploration tool for working in the third dimension. You know, we generally don't have that. I mean, we've got skarn, we've got gosens and lithocaps, those kinds of things right on the surface. But, you know, like with the Carlin deposit, you're going, well, what underlies the Carlin? Is there something else down there? So anyway, that third dimension is interesting. All right, so here they go into orogenic gold systems, super meso and hypozonal. So we know the oldest orogenic gold deposits are in Western Australia and South Africa. You know, in the Paleo-Archean or Meso. I guess that's the Mesoarchean. And then another peak at between basically in that Paleoproterozoic episode when I think we had something like plate tectonics going on. And then there was a big hiatus during the Boring Billion, right? That's warms the cockles of my heart. And then the Paleozoic distribution are more episodic. So, you know, I think there's definitely a relationship of gold with plate tectonic regimes, whether or not the supercontinent cycle is the player. And it's intriguing because there's plenty of Archean gold. So if orogenic gold equals subduction zones, then that's I think a significant argument for that something like subduction and plate tectonics was going on during the Archean. Then we got the VMSs, that's super zonal. So the earliest ones formed in the Eastern Pilbara at 3.24 billion years. So that's interesting. These very shallow things are still preserved well into the Archean. And then you got quite a few in South Africa and Australia, a little bit younger. You got the ones in Canada, right, are 2.7, right, Matt? Yeah.
Yeah, that's right. And I've actually wondered whether there might be an even earlier brief period of plate tectonics around that time. I sort of liken it, if anybody's learned how to drive a standard car, when the first few times you drive it, you don't mesh your clutch and your accelerator. And so you go, boom, 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 and then you stop, and then boom, 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 and you stop. And that's how I see plate tectonics, as bunny hopping through time.
Matt, the younger generation has no idea what a stick shift is.
Oh, okay, sorry.
Am I right, class?
No,
What's that?
no, I've driven a stick shift.
And
So
did
in the
you?
UK, it's pretty common. But yeah.
Yeah, same in New Zealand.
Okay. Well, anyway, yeah, it is interesting. I think the Archean is a really interesting time to take some of these approaches into, because obviously it's an important period in Earth history. But the simple-minded ideas about plate tectonics and mineralization, that it's all been plate tectonics, it's all supercontinent cycles, and you mineral people, if you want to find ores, listen to us. I think we're not doing them or ourselves a favor by, blindly accepting some of these ideas.
Yoo-hoo.
Okay, so anyway,
Yeah,
go ahead.
just in sort of brief comment, I forget if it was Charles Lyell or somebody that was talking about back in the early history of geology, when people did not have data from all over the world, they started off with coming up with a master plan of how everything exists, and then went out and found how it fit into it.
Yeah.
And he said, yeah, that's the wrong way to go about it.
Oh, absolutely. We have a natural tendency to want to follow our interpretations in describing our data, but real science is following the data to guide your interpretations. And that, you have to have sort of a framework to begin with, but you never fall in love with your data, but never fall in love with your interpretations. All right, so this is something.
Another way of stating that is believe in yourself, but don't believe yourself all the time.
Yeah, be your worst critic. So this is something Matt and I have been working on. So here we've got VMSs through time, right? Today we're at 0 going back, and part of what we're seeing here is the preservation of crust of different ages. But one of the interesting things you see over and over again is the record of zircons, because it's so easy to get zircon ages now. And what you can see are, igneous zircons. I think I've somehow slipped this up, because there's a peak at 1.8 that's not here, and there's a peak at 2.7 that's not here. So I think I've somehow messed this up. So sorry. All right. Then the book goes on to talk about porphyry, copper, moly systems. And porphyry, copper, moly systems are part of a mineral system that also involves high sulfidation gold, silver systems, and skarn, iron, copper, gold, moly, tin, tungsten. And they form in volcanic island and continental arcs along convergent margins. There's little disagreement with that statement. I certainly don't disagree with it. And I imagine, Matt, correct me if I'm wrong, you don't disagree with it either. So these dominate the circum-Pacific metallogeny, with the giant deposits in the Andes and in Southeast Asia and Southwest Pacific arcs. And there's also some formed in Tibet during post-collisional extension.
Yeah.
And then you find some of these in the Paleoarchean to Mesoarchean. So, I think if I was going to dig into the Archean tectonics, I think I'd rely heavily on mineral deposits as the important thing. Oops, wrong way. Okay, then the book goes on to talk about mafic intrusion hosted nickel copper PGE systems. So again, they're showing their supercontinent cycles. That's what these colored lines are. sort of funny. And then, so the PGE deposits, there's quite a few in the old times, other than the Norilsk deposit in, Russia. They're pretty much limited to these old rocks. And then the nickel copper, they're concentrated in around this plate tectonic episode. There's some in the Mesoproterozoic, and then Norilsk, it's also in there. So now these are, I wondered if these were hypozonal or mesozonal, because do you have an opinion about these, Matt? Are these really deep, or are these middle depths, or
Yeah, middle to middle upper. Yeah, I mean they crystallize at depth, but there's commonly a volcanic expression as well.
there doesn't seem to be a particular loss of these deposits
No,
in the old rocks, and that's one of the things that could be done, would be to take, the depth of these deposits and plot them as a function of age, to test the preservation hypothesis that old rocks are more eroded than young rocks. There's a lot of interesting science could be done. So here we go. Now, one of the things that can be done is looked at the large igneous provinces. So large igneous provinces are these things that happen when a mantle plume arrives at the base of the lithosphere, and it generates a big flood basalt province. And Richard Ernst, not far from Carleton, is sort of worked out a barcode for large igneous provinces with time. And you can see that there's a real density of them back in the Archean. There's plenty today, but not, according to him, as many. And, do you see a relationship between the PGEs and nickel deposits in this, the LIP record, the large igneous province record? Anybody got an opinion?
I can't see anything, but
Does anybody see a strong correlation? So that's interesting. I would have thought these big magmatic things, like the Bushveld. Where's the Bushveld? I would have thought, there it is. There's the Bushveld.
2.06. Yeah.
Yeah.
2.05.
Like the Bushveld, that's the monster. So you go, oh, that must have been a really important time of large igneous provinces. Nah, you don't. You would have thought the Bushveld would have formed here, maybe, or here. And there is a sort of an association of his barcode, and I don't know what goes into it exactly, and these deposits back here in the Mesoarchean. But as you go into the Paleoproterozoic, it's like, I don't see it, and I certainly don't see it in the Phanerozoic. So there's some really interesting things that pop up when you start comparing the mineralization record and the type, and know enough about mineralization styles to be able to subdivide them in a way that makes sense. All right, so just to finish up the nickel copper systems, book says most of them, the big ones, are preserved within 100 kilometers of the margins of cratons, and yes, they're almost certainly sourced from mantle peridotite. And they have their opinion about supercontinents. They say that many of them are associated with lips. That may be true. The relationship between large igneous provinces and these systems is not at all clear to me. But there's clearly some relation. It's not a one-to-one. But you know, the giant, the deposit of Russia, the world's largest palladium repository, is related. It's the same time as the giant Siberian lip, which happened at the end of the Permian, beginning of the Triassic. And for some reason, Mueller et al. Relate Sudbury to the incipient breakup and reassembly of Columbia, but others relate it to a meteorite impact. Is the Sudbury controversial, Matt, in your opinion?
No, it used to be, but when people thought it might be a diatreme, but that's a long time ago. The
Yeah.
only controversy I would say is whether it's a meteorite or a comet. So I had a postdoc who published a paper saying it was a comet. So
How do you tell them apart?
it related to the things like iridium and the other PGEs and their relative concentration compared to the size of the impactor that you'd need to have.
So the point was that comets
much
are
more dilute.
poorer in iridium, so that explains why.
Yeah, so the concentrations of those kinds of metals was much lower than you would expect if it was a meteorite.
Okay, interesting.
Yeah, that's if I'm remembering correctly, this argument.
All right. And then the book goes on to talk about IOCG deposits. There, we've seen this before. So they talk about Archean IOCGs, Mesoproterozoic IOCGs, and some of the younger systems. Groves et al. Suggested the formation of the giant IOCG systems was largely a result of Precambrian related to elevated activity of mantle plumes, which you would expect that Ernst's barcode would correlate with those, and I certainly don't see that. Ernst's barcode has all kinds of, let's see when it looked like there was a peak, intensity at 3.5, 2.7, 2.5, and I don't see that in this data. So, all right, then they go on to Karuna type iron phosphorus systems. Yeah. They've been grouped with IOCG deposits, but they're treated separately in this diagram. I don't understand the similarities and differences enough to discuss further. Matt, if it was up to you, would you lump IOCGs and Karunas or keep them separate?
I probably lump them together.
Yeah, it's interesting.
They're iron oxide deposits. So
Yeah.
Yeah.
And then they talk about metallic mineral systems with more limited temporal ranges. Komatiite hosted nickel copper deposits. They're largely confined to the Archean greenstone belts, although there's some in the Paleoproterozoic Cape Smith belt of Canada. I didn't know you had komateites in Paleoproterozoic. Is that something that's well known, Matt?
Yeah, it was pretty minor though, I think, volumetrically.
Yeah. And then there's lithium, cesium, tantalum, or they're called LCT pegmatites. They contrast with a different class of pegmatites. Now, this is interesting because Archean spodumene pegmatites are currently the most economic sources, according to them. And these happen in the late Mesoproterozoic and the late Neo-Archean. One at the giant Greenbushes pegmatite in Western Australia of 2.5. Tin and tungsten, greason, and quartz vein systems are Phanerozoic. Magmatic hydrothermal IRGSs are rare. We're only starting to understand them. They're saying maybe one of them is a Neoproterozoic IRGS, and they're saying maybe a Paleoproterozoic one of West Africa. and the younger Paleoproterozoic. They're saying the homestake is the homestake deposit in South Dakota is IRGS, which I had not heard that before. Have you heard that, Matt?
Nope.
And then the Carlin type deposits, which are a relatively recent kind of gold deposit, those are limited to the Cretaceous, especially Nevada. And then they're saying there's an example in the Cretaceous of China. And Matt, you said there were others in other parts of the world that last
Yeah,
time.
that's right. Yeah. Yeah,
Yeah.
there's some in the Yukon, I think.
And so these are relatively young.
Yes, relatively young.
Yeah. So the Carlin type seems to be relatively young. All right, then they go on to talk about metallic mineral systems formed in the boring billion. So this is, we talked a little bit about this. So you can see they're recognizing the differences, but they're not sure how to deal with it. Well, the boring billion, it overlaps, it embraces the Mesoproterozoic, but it goes on for 200 million years before and 200 million years after. So they're showing here some interesting things. Here's Earth's early atmosphere and tectonics. Banded iron formations are sort of limited to, the Archean. Red beds replace that as where oxidized iron is deposited. And then this is also, you see the low oxygen in detrital pyrite and uraninite in sand. So we think that, like today, we have 100% modern oxygen level. But back then, we think, prior to 2.5, there was much, much less oxygen in the atmosphere. And then this is the great oxygenation event. They've got it having more oxygen, but I don't think there's much evidence. But definitely, there's strong evidence that the Earth's exosphere changed fundamentally, sort of at this time, 2.3 or so. And we also see that in the disappearance of mass independent sulfur fractionation, because the ozone layer protects the stratosphere. And you were going to say something, Clint?
Yeah, just a minor note. It's like this has red beds, and the way they draw the diagram, it says and red beds end at the end of the Neoproterozoic. It's like, no, they're still happening.
Yeah, good point.
I-
They're
Also,
still
I wish
forming
they would
today.
use I wish they'd use GSA colors for their timeline, but I'm easy to irritate.
And also there's banded iron formations in the Phanerozoic. So
Yeah, and the Neoproterozoic too. So, but there's no question that the exogenic system and its effects on surface mineralization changed fundamentally because, especially for redox sensitive elements, because oxygen became a big player in the atmosphere. That's for sure. So this section talks about the anomalous parameters of the boring billion. So you can see them wrestling with the idea that how do we deal with this episode in Earth history? And this is what they said, that they acknowledge that this is a time devoid of gold and VMS systems, that formed during convergent margin orogenesis, even though they said previously that there were, the supercontinent in the Mesoproterozoic was surrounded by convergent margins. So with respect to the supercontinent cycle, the boring billion coincided with the final amalgamation of Columbia. That's amazing that it would take 600 million years for this supercontinent that formed at 1.8, or no, I guess a billion years. And so what they said is evidence suggests that the continental blocks within Columbia, although rotated, remained relatively discrete. So I'm not sure what that means. I think what they mean is that the continental blocks within Columbia remain pretty much where they were. So this transition between Columbia and Rodinia is got to be problematic for them. But nothing much happened in terms of orogenic gold there. So Muller et al. Suggests that instead of supercontinent breakup, there was accordion-style back arc extensional episodes with short periods of compression caused by coupling between subducting and overriding plates. That this scenario explains the rarity of subduction-related orogenic gold, VMS, and porphyry-related systems. Now, okay, I don't really see that because it looks to me like they're drawing convergent margins and back arc basins where there's plenty of opportunity for gold and VMS deposits to form.
And
But
porphyries.
yeah, well, and of course, with if you level the preservation argument against understanding tectonics on the backs of ore deposits, then they'll say, well, those are the ones that are going to get removed first. And it's like, okay, actually agree with them. So now, accordion style tectonics. Now I'm familiar with plate tectonics, and I'm familiar with single lid tectonics to a certain extent. But this idea of accordion style tectonics, I'm familiar with accordion. It's a kind of musical instrument nobody wants to hear. But I just don't understand what is accordion style tectonics. And that's it's so important if you have an idea to explain your idea. All right, so and they go on and note that even though the boring billion was relatively calm time in terms of many Earth processes, it was not so boring billion in terms of its mineral systems and the anomalously rich mineral endowment. So they list the giant deposits of the boring billion, and basically there's quite a few. So they're not saying it was boring in terms of ore deposits. All right. So then they go on and talk about mineral systems that extended from the Archean Paleoproterozoic into the boring billion, which included the Mesoproterozoic IOCG, Karuna type irons, mafic intrusion-related nickel, copper, PGE, and carbonatite hosted rare earth systems. And then they say things like formation of Mesoproterozoic IOCG systems is consistent with accordion style tectonic. Okay, we don't know what that means. Extension would have caused a mantle plume related to hot asthenosphere uprise, causing intracordonic A-type magmatism and associated magmatic hydrothermal activity, I guess to make IOCGs. Okay. And then the Karuna, the Paleoproterozoic Karuna, but there's other ones that extend into P Ridge and Benson. Most intrusion-related nickel, copper, PG systems formed during supercontinents Columbia and Rodinia. Now, a lot of this is they're trying to force these ore deposits into their model. But the thing that's particularly interesting to me is these carbonatite rare earth systems, which we have two big ones. And one of them is the Bayan Obo, which is not mentioned here. And the other one is Mountain Pass, the one in the United States. And these are both about 1.4. They formed in the Mesoproterozoic. But there are other examples. As you guys have seen that rare earths continue to be in the news. Trump had this big agreement with China, and they've agreed to stop export bans on rare earths. But that's going to continue. It's going to go back and forth. The Chinese have found You know, the United States is very sensitive to what we do with our rare earth resources. So there's gonna, and you know that the US Defense Department has invested in a Mountain Pass because they really do want a reliable supply of rare earths for defense purposes. And you know, going, okay, well, maybe what we need to do is focus on the Mesoproterozoic to find more of these rare earths. Now, that makes it sort of national significance to try and figure out more about these two big Mesoproterozoic rare earth. Mesoproterozoic, so mineral systems largely confined to the boring billion, world-class to supergiant SEDEX deposits. Now this one was a little puzzling to me because I thought there were plenty of SEDEX deposits of younger age. So, Matt, can you tell me
Yes.
whether they're confused or I'm confused?
No, I think, well, it depends on what you call world-class to supergiant, right? That's a definition problem. You know, there's lots of SEDEX deposits in the Yukon, for example, which are Paleozoic. Yeah. So yeah, some of those are quite large.
Yeah, I'm holding my, this was curious. I never really thought that SEDEX was sort of focused on the Mesoproterozoic, but maybe it is.
Yeah, I mean, it may be common in the Mesoproterozoic, but it's certainly not focused on.
Well, I don't know enough about Broken Hill to have an opinion about what they say in that last sentence. It says it is controversial whether the supergiant silver-rich Broken Hill deposit of Australia is part of the SEDEX group or represents a second BHT deposit, BHT type deposit. Yeah, that's just what we need is another type of ore deposit. So have you heard of Broken Hill, which is, you know, obviously one of the, you know, textbook ore deposits on the planet? Have you heard of it as being a SEDEX?
Well, yeah, lumpers and splitters, but yeah, some people consider it a SEDEX and some people consider it its own sort of intermediate between an MVT and a SEDEX, or no, between a SEDEX and a PMS. But how can you have a Broken Hill deposit that represents a second Broken Hill type deposit? That doesn't make sense to me.
No. I think what he's saying is maybe we should consider breaking out another group of deposits that's not quite SEDEX and call them Broken Hill type deposits.
Okay. All right. Yes. Okay. That makes more sense. My misreading.
So to me, this field is in a very immature state, you know, of how many kinds of ore deposits are there. And I think, you know, we see this over and over again, like with meteorites, you know, people started classifying meteorites based on this or that. And then the question is, well, how do they relate? And that's a more difficult problem. But I think that we're seeing just some of the confusion that's in the industry about how to break out different kinds of ore deposits, which makes sense given how many different elements we're dealing with. Now, the unconformity type uranium systems are restricted to the boring billion. The largest are in the Athabasca Basin in Saskatchewan, world's largest uranium resource, excluding those of Olympic Dam. Now that surprised me because I saw them talking about Broken Hill. That's different than Olympic Dam. Well, there's another thing I don't understand. Olympic
Dam's an IOCG, right? But it's the concentration of uranium is fairly low compared to Saskatchewan. Those ones are really rich, high grade, but Olympic Dam is just so massive that it has an awful lot of uranium. So it's
even though
low grade, high
abundances.
tonnage.
Yeah. Okay. And so these formed around 1.6 billion years ago. These unconformity type uranium systems are consistent with formation and preservation in rifts with less oxygenated environments where major redox boundaries were defined by graphite bearing basement overlain by more oxidized sedimentary units. Okay, so even though the great oxygenation event happened, there was still, it still was nowhere near the amount of oxygen that we have today. So that's an interesting observation. So it shows the relative positions of mineral systems in reconstructed Columbia during the boring billion. So Columbia, of course, is the supercontinent. So this is the way they put it together. I don't know how confident people are in these juxtapositions. You notice here they've got a very nice long convergent margin, and yet none of the rocks that we've looked at really look like convergent margin mineral deposits. There's Mountain Pass right on the edge of Laurentia. Looks like it's very close to a convergent plate margin. And I don't think that a carbonatite like rare earth deposit would be associated with a convergent plate margin at all. Bionoble is not so far away either. And then this is how they put them all in there. But it is interesting. This is where they've got thick lithosphere suggesting that this is a craton. These are actually outcropping cratons in purple. And you do see the concentration of these ore deposits close to the craton edge. That's a point they make over and over again, is that, there's for some reason, favorable sites for mineral deposits are near craton edges, other than Broken Hill. There's Broken Hill, and there's Olympic Dam. So they talk briefly about diamonds. There are not that many kimberlites in the Mesoproterozoic, as we talked about, but two of the big ones are in the boring billion. The Argyle deposit in Western Australia and the Premier in South Africa. Now we didn't talk about Canadian kimberlites, but those are like mostly Eocene, right?
Yeah, much younger.
Yeah, they're really young, and those clearly seem to be related to subduction beneath Western North America. That's the general sense of that community, to your knowledge, Matt, or am I making it up?
Yeah, you're getting a little outside my ken there.
Okay. All right, so there are some diamonds they want to talk about. And then, of course, the two big rare earth systems that are in the news. And these formed Bionoble's geochronology has been very challenging. But the general consensus now is that it formed somewhere in the Mesoproterozoic, and then about the same time as Mountain Pass. So if Bill Gates gave me, let's say $10 million to go explore for rare earths, I would say, well, let's set up the Mesoproterozoic research group. So and then the book goes on to talk about the not so boring metallogeny of the boring billion, and they talk about it being a metallogenic bonanza that yielded some of the world's largest ore deposits, rich in copper, zinc, silver, lead, and gold in SEDEX, BHT, and IOCG deposits, uranium and unconformity type and IOCG deposits, rare earths and carbonatites, diamond and lamproites. What's noticeably missing from there is the group of mineralizing systems that we have no trouble relating to subduction and plate tectonics, right? Orogenic gold, porphyry coppers, those sorts of things. It is quite interesting. and I think worthy of further study. So they talk about the SEDEX systems formed in rift basins on the margins of thick lithosphere in the boring billion. That's interesting. Were succeeded by Phanerozoic SEDEX deposits formed in faulted passive continental margin settings. So they're acknowledging something different between the SEDEX system between the Mesoproterozoic and today. Now, this is interesting. You know, you get little hints about Broken Hill. The Broken Hill type systems appear to have formed in freshwater rift subbasins with anomalously high heat flow. So, and then they go on and say, and I had to bold this, there is therefore within the boring billion a compelling correlation between unusual tectonics and anomalous mineral systems and their giant endowments that mark its metallic mineral bonanza. It's like, I can agree with that statement. Why do they keep going back to plate tectonics all the time? All right, then they go on to the metallic mineral systems and the great oxidation and explosion of life events. So we've been talking, focusing on endogenic systems, which are largely controlled by the cooling of Earth's interior, changing tectonic styles. And we've discussed that, but another event that severely affected this atmosphere, hydrosphere, biosphere system was the continuous increase in atmospheric oxygen. And that was especially important for redox sensitive elements of especially exogenic, so sedimentary, placer, some hydrothermal metallic mineral deposits. And that's what's being discussed in this section. So here we go back to the oxygenation event, the great oxygenation event, and the Neoproterozoic. So this is a log scale, and it's very poorly constrained, by the way. But the general impression that there was very little oxygen in the atmosphere or the hydrosphere in the Archean, and that increased significantly about 2.3 billion years ago, and that there was another jump just before the Phanerozoic that made large metazoans possible. And as we know, that the oxygen in especially fluids is critical because it controls the metal solubility and stability of ore minerals and the redox sensitive metals, and that's especially iron, manganese, and uranium. And the oxygen in the atmosphere controls the oxygen in the hydrosphere. So, these things are going to precipitate underwater for the most part. So, and then there are interesting feedbacks with life that they talk about in here that I hadn't really thought about. And they mentioned that, the increased diversity of life forms led to changes in weathering, led to deposition of biogenic sedimentary rocks as some preferred sites for reaction with ore fluids, and the carbonaceous sedimentary shales that are very reactive. They absorb metals, they provide metal sources, and they can catalyze hydrothermal redox reactions. So the proliferation of life in the last 600 million years also had a big effect on especially the exogenic mineralization systems. So now we're looking at, these are the exogenic ones. I can see that with a BIF, iron, manganese, yes, uranium, yes. I'm not sure about Carlin type gold, why it's in this group. And regolith hosted systems, that's like, laterites and bauxites and things like that. Those are, extreme weathering projects. So it's nice to see there's no supercontinent cycle here. And what you can see is these things become more common in the Phanerozoic when there's more oxygen. So this influence of the great oxygenation event at 2.4 or so was especially important in terms of the iron required for the Industrial Revolution. Modern iron ore mining is dominated by enriched low phosphorus ores derived from oxide facies banded iron formations in the great Biff basins of Western Australia, Brazil, Africa. The iron ores that fed England, I'm not sure exactly where they came from. I don't think they came from there. They came from somewhere else. But there was enough iron back then. So these major Biff basins formed between, right at the Archean Paleoproterozoic boundary. And these formed on passive continental margins from silica and iron-rich ocean waters enriched from submarine hydrothermal activity. And, the increase of oxygen in the water, turned all of the soluble divalent iron into insoluble trivalent iron, which settled the seafloor as the Biffs. So, and that's the main reason that there are very few, there are some, but not very many banded iron formations after 2 billion years. Sedimentary manganese deposits, they're responding similarly. They were deposited relatively late. So there are some Paleoproterozoic manganese resources in the Transvaal group of South Africa. But a lot of them are concentrated in the Neoproterozoic to today, with a peak in the late Mesozoic, Cenozoic, including the giant Oligocene iron ores of Ukraine. So sedimentary uranium deposits. Before the great oxygenation event, there was detrital uraninite or pitchblende. So that's UO2, so it's +4 uranium. So that is relatively reduced. And then after that, they're dominated by the unconformity types with diagenetic uraninite, not detrital uraninite. So that forms underground where the oxygen fugacity is going to be lower than it will be at the surface. And then following that, the Phanerozoic roll type uranium deposits, like those of South Texas, those are also diagenetic. And right, so we already know what the Texas uranium deposits are. And then the influence of the Neoproterozoic oxidation event and the Cambrian explosion of life, the explosion of complex life in the last 500 million years created much more carbonate rocks and carbon-rich black shales. And those carbonate rocks played an increasingly important role in providing reactive rocks to interact with circulating ore fluids and produce replacement style mineral deposits. And then carbonaceous shales contain an abundance of metals. These rocks became increasingly important in providing both sources of metals and providing redox fronts for fluid reduction and sites of metal deposition. And this gets us to sediment hosted lead zinc deposits. A major effect of rising atmosphere and hydrospheric oxygen and the Cambrian explosion of life was the contrasting temporal patterns of SEDEX and Mississippi Valley type zinc lead deposits. And here they keep saying things, a combination of change in geodynamic regimes in the boring billion, which is like, okay, led to significantly different peaks in temperature distribution. 1200 million. The peak development of SEDEX was in the boring billion, but the MVTs become dominant after the Cambrian. So the explosion of life during the assembly of Gondwana, I'm not sure why that matters. Also caused the rise in oncolytic and oolitic manganese systems, an increase in global skarn, iron, copper, gold, moly systems in carbonate host rocks, and carbonate hosted Carlin type gold silver deposits. I didn't know there was that much silver in Carlin deposits. So that global increase in carbonaceous shales after the Cambrian provide widespread reductants, carbon, resulting in the development of sandstone front roll type uranium systems and perhaps enhanced Phanerozoic sediment hosted orogenic and Carlin type gold. Late Neoproterozoic stratiform copper cobalt deposits also formed in petroleum bearing intercontinental rift basin. Coal deposits, and sometimes coal seams host gallium deposits in China. And coal may also have been important for the nickel copper PGE mineralization in the supergiant Norilsk mafic intrusion of Russia. That the interaction of that magma with coal deposits is thought to have done some crazy things. And then the oxygenated atmosphere also caused more severe weathering to produce bauxites and nickel copper laterite deposits. It also caused supergene upgrading of copper and gold grades of porphyry, copper, gold, and orogenic gold deposits, and also helped form some of these placers. And some heavy rare earth deposits also form by rare, intense weathering. So the book, this chapter, a very interesting chapter, summarizes the most productive times in Earth history. And they acknowledge many mineral systems only form at certain times in Earth history. When that was depends on 5 factors, which affect endogenic and exogenic mineralization systems differently. The progressive cooling of the hot Earth, you're going to have less melting, and that's going to have some effect on magmatic mineral systems. Tectonic styles and events at different times in Earth history that will affect the endogenic. I think they're implying the supercontinent cycle in there, but they don't state it. The progressive oxidation of Earth's atmosphere is obviously a big control, especially the exogenic mineralization, the biological activity in the hydrosphere, and the preservation from erosion, which is going to affect the exogenic and the shallow endogenic. So they go on and talk about the mineralization controlled by the cooling Earth, and the importance of that for controlling the nickel copper PGE magmatic systems. The earliest being the ones that are dominated with komatiites, which only occur in the early part of Earth history. And 2.7 to 2.2 emplacement of the giant layered intrusions and giant deposits of PGEs and titanium, chromium, and iron. Interesting. That doesn't include Bushveld, which is at 2.0. And that definitely is one that should be in there. And then we've got the periodic formation of magmatic mafic intrusion, nickel copper PGE in the younger period, and the possibility that lithium and tantalum bearing spodumene pegmatites may also be most widespread in the hotter Mesoarchean to Neoarchean Earth. I don't really understand why these old pegmatites are such valuable resources, but they are. So, then they go on to talk about tectonic style and events. Muller et al. Argued for plate tectonics from the Mesoarchean to the Cenozoic and for the importance of the supercontinent cycle for controlling mineralization. And we've already gone over why I disagree with them. And it is worth noting that Archean mineralization is more similar to Neoproterozoic and younger mineralization than Mesoproterozoic mineralization. And I agree that resolving the controversy about Earth's tectonic history is essential for understanding, especially endogenic mineralization through time. Then they talk, summarize the role of progressive oxidation of the atmosphere and the biosphere. And they talk about the control of that on the BIF provinces and the widespread Cenozoic weathering in tropical climates in an oxygen-rich environment. And then in terms of mineral exploration, the weathering also produces negative effects with the surface expression of mineral deposits obscured by thick regolith profiles. When you're dealing with exploration in tropical regions, you've got to have a different strategy than you do in desert or glaciated regions. Biological activity definitely increased the abundance of reactive carbonate rocks and carbon-rich black shales. The increasing abundance of Phanerozoic carbonate rocks, especially reefs, favored MVT systems, and also provided important hosts for the Carlin-type gold systems, and skarns and skarn mineralization became more important as a result of more and more carbonate rocks. Then preservation from erosion is the final factor that, of course, if once an ore deposit has been eroded, you can't find it. And because of erosions, the deep mineralizations like graphite, orogenic gold, and interesting VMS, I'm not sure how that got in there. That VMS doesn't seem like deep mineralization to me, are more likely to be preserved than shallow mineralizations. It would be interesting to subdivide the ore deposits of Earth into those groups and see what is the relationship between age and deep mineralizations versus shallow mineralizations.